Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 33 in our incredible new tutorial series where you're learning how to think like an engineer using the Arduino Uno R4 Wi-Fi. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee, poured over ice, no sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Sunfounder Elite Explorer Kit. Now, hopefully most of you guys already have your gear, but if you don't, take a look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot simpler if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to do is I'm going to teach you how to use a really super cool little component in your kit known as a photoresistor. What does a photoresistor do? Its resistance changes in response to the intensity of light. How would you maybe use one of these things? Well, a practical thing, they're used in like the security lights around your house. You don't want to leave the lights on all day, wearing out your bulb and wasting electricity, and you don't remember to turn them on and off. And so what do you have? A little photoresistor, and it sees that it's getting dark. It turns your lights on. It sees up, it's morning time, turns the lights off. Now you could think, oh, we'll put them on a timer, but a timer is really not going to work because when you don't live on the equator, there's long days and short days. And so what is the ideal solution? A photo detector. You might also use it to open and close the door on a chicken coop. So you let the chickens in, you let the chickens out at dawn, and you close the chickens up at dusk. And so there's all types of applications where you would use a photoresistor. And so I am going to show you how that super important little component works today. Hope that sounds like fun. So let's come over here, and I need to show you the photo detector, and I have mine from the kit here. It's in that little bag of goodies in your kit, that little plastic sack. You can go in there, you can find it. It's got a little window, and it has this serpentine pattern. And then if you look at it, it has two leads on it. And so that is your photoresistor. How does the photoresistor work, you ask? Well, that is what I am going to show you today. So I will get out of your way. I will have another sip of coffee. And we will come over here to the old sketch pad so I can show you how this works. Okay, the photoresistor is a semiconductor device. What is a semiconductor device? Well, you have conductors like metal. Metal has a lot of free electrons, and so it's very conductive. Its conductivity is high, easy for the electrons to move through it, and its resistance is, the conductivity is high, it's conductive, and the resistance is low. It's not resistive, it is conductive. Then you have insulators, things like glass or plastic. They don't have free electrons, and so therefore their resistance is very, very high, and their conductivity is very, very low because there's no free electrons in those materials to carry the current. So we have conductors, we have insulators, but then we have this magical material in between, which is a semiconductor. A good example of a semiconductor is a silicon crystal. Now we know that all computer chips are made on semiconductor material, most on silicon. And so silicon is used to make electronic components like microprocessors, microcontrollers, memories, and everything. And in their simplest form, they are used to make photodetectors. So how does that work? So let me come over here and let's see if I can draw that. So what I'm going to do is I'm going to draw a length of a semiconductor material. So I come here, and the thing about a semiconductor material is every point along the length of the semiconductor, there are different energy levels. There are different energy levels that the electrons can be at. And so I will start by showing these energy levels, and these energy levels are all allowed. These down here. These energy levels from here to here are all allowed. And what is that range of energy levels called? What is that band of allowed energy levels called? It is called the valence band. The valence band. Okay. Now, in addition to the valence band up here, we also have energy states up here, and these energy states that are allowed between here and here are called the conduction band. Conduction band. So the electrons can be in the valence band or the electrons can be in the conduction band. But between the conduction band and the valence band is an energy gap. And this is also called the forbidden region, that at those energy levels in the energy gap, electrons are not allowed to be at those energy levels. So the electron either is going to be in the conduction band or it's going to be in the valence band, but it can't be in between them. Now, there is sort of a universal law of physics that in all physical systems, it wants to seek the lowest energy level. So if you have electrons, they're all going to want to fall down to the lowest energy level. It's sort of like if you have a bowl and you put a marble in it, what will it do? Every time it might move around, but it's always going to end up at the bottom because that is the lowest energy level. And you never have it stop on the side because that's a higher energy level and it can just roll down to the bottom. And so that is exactly what happens in these semiconductor devices. Where are the low energy states? The lower ones are in the valence band. So where are the electrons going to fall down into? They are going to go and fall into the valence band, and they are going to fill up those allowed energy states in the valence band like this. I'll just draw a couple of rows. You know, this is a simplified picture. They are bazillions of different electrons down in the valence band, but I will draw 10 just for the purpose of illustration. So now all the electrons fall down, they fill up all those energy states in the valence band, and that's where your electrons are. So what do we have up in the conduction band? We have energy states that are there, but they are empty. So I will draw those like this. Okay, what am I drawing? Empty energy states. They could hold an electron, but why is there no electron? Just for the same reason that you don't have a marble on the side of a bowl. Okay, they've all fallen down into the valence band. So now let's say that we hooked a wire up to the two sides of this. So I'm going to put a wire. That is not a good color for a wire. Okay, I'm going to put a wire here, and then I'm going to put a wire here. Okay, and now if I put a voltage across here, would I have any conduction? Now you might say, well, yeah, because you got all of those electrons down in the valence band. But this is what I want you to think about. I want you to think about the valence band as a room, and the room has two doors on it, one on each side. So you have a room with two doors on it. Now the electron, I want you to think of the electrons as being people. And so now I want you to think of that room with a door here and a door here, and that room is completely filled with people. Well, if I come up to the door as a person and I want to go from this door across the room to this door, can I do it? No. Why? The room is filled with people. all the little allowed spaces have been filled up. So there's no room for me who wants to take current across the device. There's no way for me to get in, and there's no way for me to find my way across. Now you would say, well, what about the conduction band up here? It's all empty. It would be easy to walk across there. Yeah, it would be easy to walk across there, but the problem is I'm not up there. I'm down at that lower energy level. Why? All the electrons want to be at the low energy level. So you see, there's a lot of energy levels. There's a lot of electrons, but the room is packed. And then there's a lot of space to move around, but the room is empty. So this semiconductor device, as it's pictured here, is going to carry no current because it has no conductivity and its resistance is very, very high. Now, what happens if I shine light on the semiconductor device? Light is little packets of energy called photons. And so for the sake of this illustration, my photon is going to be purple. What is a photon? It is a packet of energy. It is a packet of light energy. And so that photon is going to come in and it is going to hit this semiconductor device. And what is it going to do? It is going to the energy of that photon is going to be absorbed, and that absorbed energy of the photon is going to kick an electron from the valence band to the conduction band. So that electron comes up here, and then what is left down here? A hole is left down here. I'll make a hole solid green so you can see. So I have a hole here and I have an electron here. Now think about that electron up in that empty room. Whoosh, he can carry current. He can become current through there. And then what about this hole? Well, now remember our crowded room problem in the bottom? Now I've got one spot that I can step into, and then I can step across on that spot. So this is the way that you can think of the valence band. So you're going to be conducting current in both the conduction band and the valence band. But let's think of that valence band because it's a little harder to think of, but I want you to think of a plumber's level. A plumber's level is filled with what? It is filled with water. And then what does it have? It has a bubble. It has a little air bubble. What is an air bubble? It is an absence of water. Now, as you tilt the thing, what you see is you see the bubble move back and forth. And you think of the bubble as a real object, but really it's the water moving. And what you're doing is just looking at the empty spot, the vacant spot move around. Well, it's the same thing down in the valence band. You can think that it's filled with water and there's one little hole. And rather than thinking about all the electrons moving around, you can just think of that hole moving around. And so what this hole is free to move here, okay? And then what happens? The hole moves here, and then this becomes filled. Now, did that hole really move? Well, no, what really moved is the electron moved. But all the electrons moving is too hard to keep track of, so we just conceptually we think of a hole. So now what do I have? This hole can conduct electricity, and this electron up here can conduct electricity. So all of a sudden I've gone from being completely insulating to now having a little bit of an ability to carry current. Well, if I wanted to carry more current, what would I need? I would need more electron hole pairs. And so what I would need to do is I would need to turn up the intensity of the light, and I would need to start sending in more photons. As more photons come in, what am I going to have? I'm going to have more electrons jumping up or being kicked up to the conduction band. So now you can see if I had 3 times as many electrons, I would have 3 times as much conductivity. I would have 3 times less resistance. And then, like I say, you're having then these holes down here that can also conduct electricity. So basically, the more light that I have, the more electron hole pairs that are generated, and the more electron hole pairs that I have, the more current I can conduct. And so let's look at this kind of like a bottom line type thing. So what happens is, if I have more photons, that means brighter light, more photons, tell me what I'm going to get. I'm going to get more electrons in the conduction band, more electrons in the conduction band, and I'm going to get what? I'm going to get more holes in the valence band, and then what am I going to get? I'm going to get more conduction, and then I'm going to get less resistance. Okay, so that's the physics, but let's think practically. More photons means brighter light. So the bottom line of the bottom line is, as the brightness of my light goes up, the resistance of my device, the resistance is going to go down. Okay, so that, my friend, is 10 minutes of solid state physics. You couldn't see less resistance there, so you understand that. Okay, so let's come in here and let's see how this works practically. So we're going to switch back over. We are going to switch back over to this most excellent view. And now what you see is, you see this Mr. Photoresistor in a whole new light, knowing that that little serpentine strip there is a semiconductor material, and because of the little glass window, it is exposed to the light. Now, what I'm going to show you here is, you don't need this to do this lesson, and you don't need this to do this class, but this is a digital voltmeter, and if you don't have one, they are very, very handy. And kind of like if you have an Arduino kit or you have a Raspberry Pi kit, the first thing that you should get after the kit is one of these digital voltmeters, because this thing can measure DC voltage, AC voltage, DC current, AC current, and it can measure resistance, and it can check diodes. And so it is probably the most bang for your buck as far as adding something to your lab. I have a link down in the description to the one that I am using. If you don't have the coins for it right now, don't worry. You can look at me use mine, and you can completely do all the homework without having one of these. If you do have a few coins laying around, this is very useful. I also bought, and I'll leave the link to it, it has the connectors and cables with it, but I find these little extra ones very useful, because the ones that come with it are more for like doing electrician work, and these little clip-on ones are very, very good for working with your electronic board. So let's see. I'm going to start by kind of putting all my lights on, and so I've got studio lights, and then I have a little light that lights my bench top here. So I kind of have all of my lights on. And now what I'm going to want to do is, I am going to want to measure resistance. So I'm going to turn this up to where you see ohms, and then I've got my two cables plugged in. And then the first thing that you see that it reads is, it is reading OL, and that means overload. That means infinite resistance and zero conductivity. Why? Because these are not connected to anything, so there's no conduction. Well, what I'm going to do is, I'm going to come in, and this is what's neat about these extra cables. Do you see how it has that little clip that comes out, and this is spring loaded? So I can come on and just clip it to that and get a very, very secure connection. And then I can come in and clip it to this like that. I can't see it because my hand's in the way there. And so now I've clipped those two things together. And in bright light, what does this say that the resistance of this is? It says it is 0.7 K ohm. So that's 0.7 thousand ohms. What would be 0.7 of 1,000? That would be 700. So really, in this bright light, the resistance is very low. It's about 700 ohms. Okay, now you tell me, what do you expect to happen if I turn the light off? Well, just like I said here, if I say the light goes down, then what do I expect? I expect the opposite. I expect the resistance to go up. So I started with the lights on, and now if I turn the lights off, I expect the resistance to go up. And so let me come in here, and the first thing, the light that is lighting up my my little bench top there, I'm going to turn that off. And when I do, wow, I went from 700 ohms to 1000 ohms. So by turning that light off, my resistance went up by 30%. And that, in electronic terms, is really a huge signal. Now you can still see I am illuminated, so you can see that my studio lights are still on, but I'm going to come in, and now I'm going to turn my studio lights off. And then what happens, I went from 1000 ohms to 3500 ohms. So I've gone from 600 up to 3000. That's like a 50 times increase in the resistance. And now you can see I'm still not really in the dark, but if I come in and I start covering this thing up, I'm getting up to like maybe 50,000 ohms, and it's still not complete darkness. I would guess if I made this completely dark, it would probably be about 100,000 ohms. So I've got 100,000 ohms, and let's say on the low end, sort of like round 700 or 600, round that to 1,000. So somewhere between 1,000 ohms and 100,000 ohms, depending on how bright the light is. And so that is really, really extremely sensitive, and you can also see it's very responsive, and it's also very stable. So as I am holding the light constant, you can see that the signal is constant down to something like about an ohm. So that is really, really, really cool. Well, now how am I going to get that to work in a circuit? You know, how can I take advantage of that in a circuit? Well, what I have to do is I've got to create a voltage divider. Okay, I've got to create a voltage divider. And as much as I like my solid state physics here, I must sadly say that I'm going to have to clear it to make room now for a circuit. So the way that you make a voltage divider, what I am going to do is I'm going to have, first of all, this photoresistor. And how would I draw a photoresistor? I would kind of draw it like this, like a resistor, and I would put the glass window around it, and then I would show the photon coming in. So you see that little squiggly line is like a photon. The photon's coming in and hitting the resistor through a window. That is how you would have a schematic of the photoresistor. Now I'm going to have a bias resistor down here, like this, okay? And then what I'm going to do is I'm going to put 5 volts up here, and then I'm going to measure the voltage here. And I'm going to call this V out. How can I measure it? Well, with one of the analog pins on the Arduino, right? With one of the analog pins on the Arduino, I would be able to measure that. Okay, so now how do we do a little circuit analysis on this? What do we expect V out to do as the light gets brighter, and what do we expect V out to do as the light gets dimmer or darker? And you got to remember that V out will always be between, this is the ground, so it will always be between 0 and 5 volts. But how is it going to behave? Well, what we know is the voltage, according to Ohm's law, is the current times the resistance. And when you have 2 resistors in series like that, the total resistance is the sum of the 2 different resistors. So what is my V? My total V is 5 volts, and that is going to be equal to the current that we are going to calculate times the total resistance. And the total resistance is this resistor plus this resistor. So we'll call the one RP for the resistance of the photodetector, plus the R1 which is just the bias resistor that we put in R1. Now, what should R1 be? Well, the R photodetector is going kind of between, let's just say, roughly 0 ohms and 100,000 ohms. So this bias resistor should be kind of in the middle there. So you could imagine using 50,000 ohms. A nice convenient one that I used was 10,000 ohms. Okay, 10,000 ohm resistor down here, or you could call that 10K ohm, like that. So now what do I have? I have 5 is equal to I times R of the photodetector plus R1, and that R1 we know is 10,000, like that. Now what is the current through that circuit? The current, divide both sides by RP plus 10,000. So that would be, the current is going to be 5 divided by RP plus 10,000. Okay, that's the current. Now what is V out going to be? Well, V out is going to be equal to, V out is going to be equal to I, which we just calculated, times R1. So V out is going to be equal to R1. And what is R1? That is 10,000 times I. And what is I? I is here. So that would be 5, and then divided by R of the photodetector plus 10,000. Okay, and so this gives us the V out. Now, let's just say that the light is very, very bright, and therefore RP would be 0. Then what would I read? I would have 10,000 over 10,000, which is 1 times 5. And so if the light's very bright here, I should read about 5 volts. Now, what if the light is very, very dark? Then RP is going to be like 100,000. And so you have 5 times 10,000 over 100,000. That is going to be almost 0 volts. So I'm going to go from almost 0 volts when it is dark up to almost 5 volts when it is very, very bright. Does that make sense? So now let's think, what is voltage going to do? And we're going to measure this voltage at V out, right? We're going to measure this V out using the Arduino analog pin. And what is it going to do? Well, as the light gets brighter, what is RP going to do as the light gets brighter? RP is going to be getting smaller and smaller and smaller, and therefore the V out is going to be getting bigger and bigger and bigger. Now, as the light gets smaller, RP, as the light gets higher, V out gets higher. As the light gets smaller and smaller and smaller, what's happening? This gets bigger and bigger and bigger, and therefore V out goes down. Okay, so as the light gets bigger, V out should get bigger. As the light gets dimmer, I hate it when I cover that up like that. So as the light gets dimmer, V out is going to get lower. Okay, does that make sense? And that is the wrong one. There we go. Okay, we've recovered from that. Okay, so now let's come back over here and let's see if we can go ahead and hook that up. So what I have is, that is not the view that I want. Let's come over here. Okay, so now I'm going to take this voltage DVM off of here, and now I'm going to build a little circuit. All right, so you can see over here I have my Arduino, and what I have is, let's get this hooked up very, very carefully. These are kind of, I want to get these a little bit neater hooked up. So what do I have? Right here, I have a 10,000 ohm resistor. And then the lower leg of the resistor, through the black wire, comes over and connects to ground. Okay, do you see that black wire is connected to G and D, and the red wire is connected to 5 volts. So I have the black wire to ground and the red wire to 5 volts. And then this other leg of the resistor, is connected to A0. Okay, so what am I doing? I'm basically showing you how I hooked this circuit up. The top leg of the photodetector goes to 5 volts. The bottom leg of the photoresistor goes to one leg of R1 and then comes to V out, which is pin A0, and then the lower leg of the resistor is grounded. So let's come over here and let's watch this. Now, you know, you guys that are good at building circuits are going to understand this really easily. You know, yeah, I've got my light back on there. So here, the lower leg of the resistor from the picture goes to ground. The upper leg of the resistor goes to A0. And then what I've got to do now is I've got to connect this from the top of the resistor over to the 5 volts. Okay, so can you see that? This leg goes to 5 volts. This leg goes to A0 and goes to the resistor, and then the other side of the resistor goes down to the ground. Okay, so hopefully that makes sense. Let's see if I can back this off a little bit now so you can see it a little better. Okay, so that is our circuit. Now we have to come in and we got to code this thing up. Okay, we got to come in now and we got to code this thing up. So basically, what do we want to do? We want to read this voltage right here at A0. And this thing being askew, everything is askew. I can't stand things being askew. Sometimes I thought, what if I just had a video once and that I spent the entire hour of the video trying to get everything perfectly square, and how some people would be so angry, but some people would say, no, get it square. Don't go on till it's square. I guess those are the two types of people in the world, and you're probably one of them. Okay, I promise I'm not going to do that. Okay, we're going to call that good. No, it's not good. There, that's good. That's perfect. We're going to switch off of that before I decide that it's not perfect. Okay, so now what are we going to do? We're going to come in and we're going to measure that voltage at A0. So what are we going to need to do? The first thing we're going to need to do is set up some variables. And so I'm going to have the light pin, which we connected to A0. A0, like that. Okay, then I'm going to be reading from that voltage, right? The voltage of that pin, and what I'm going to call, that was just the meter saying I'm turning off. So that is going to be the light val. That's going to be the value that I read. That's going to be a variable. I'm not putting any number into it, but I'm just declaring the variable. And then let's see, what else do I need to do? I think that's about all that I need to do. So now I'm going to come down in the void setup, and we're probably going to need to do our pin modes here. So my pin mode, which pin? Light pin, and it's going to be a what? It is going to be an input like that. Okay. I've been programming the Raspberry Pi Pico for the last 6 months. So it's going to take me a while to remember to put my semicolons in. I've got to get back in my Arduino zone, so you guys be patient with me. So I did the pin mode as light pin input. Now I'm going to print some things out. So I'm going to say serial.begin, and let's do 115.200 just because we can. Not a comma there, 115.200. We used to always use 9600, but now USB is really very reliable up to the 115.200 I have found. Now we're going to come down to our void loop, and what am I going to do? I'm going to do an analog read, right? We learned this earlier. Light val is equal to analog read, so I'm going to read that light pin, which is pin A0, light pin like that. I'm going to read that. Now, after I read it, what should I do? Let's just do a serial.print What are we going to print? What we just read, light val. Okay, like that. And then let's just put a delay of 100 milliseconds like that, just to give it a little bit of time. And now, what do we expect? What do we expect? Let me come back over here. Okay, what do we expect if this works properly? Okay, what do we expect? We expect as the light goes up, as the light gets brighter, the V out should go up. And as the light gets dimmer, V out should go down. And so let's see if the world is in proper order and if in fact this thing operates like that. And we're going to come back over here at this. And I think we're going to run it. So I will need everyone to hold their breath. Oh, come on. Oh, D9, what? Serial uppercase S, rookie mistake, hold your breath. Okay, it's going. It's looking good. Looking good. It is downloading, 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 and boom, it's done. So now we're going to come over here, and I'm going to turn on the serial monitor. I'm going to turn on the serial monitor. And then why is it not happy? Somebody tell me why I'm getting these strange question marks and cubes. Why am I getting that? Because I set my baud rate to 115/200 and the serial monitor was set to 9600. So we're going to come down here and we're going to go on up to the, where is it? 115/200 like that. And then we might need to kind of turn it off and turn it on again. And look at that. I'm getting a bunch of numbers going across the screen. What did I do wrong? Someone tell me what I did wrong. I did a serial print, which just keeps printing, and I needed to do a what? Serial print LN. Why am I doing these things? Because these are common mistakes that you guys make, so I'm just reminding you how to debug these common mistakes. The things you're seeing here might or might not be, these things might or might not be intentional mistakes. All right. So now I'm going to turn the light off, and it's not 947 volts, right? We read from 0 to 1023. So 1023 would be 5 volts and 0 would be 0. So if I'm reading 947, I'm reading a pretty high voltage, something getting pretty close to 5. But now if I turn the light off, what do we expect to happen? We expect it to go down, and boom, it went down from 947 to 921. 947, 921. Well, that's not a very big change. It's not a huge change, but you see there's still a whole lot of light in the room. Like you see when that desktop light goes off, there's still a lot of light in the room. And so there's certainly a completely discernible signal from that one going off. But now let's turn the studio lights off. And when I do that, boom, I go down to 780. And now if I cover up with my hand, I'm getting down to even lower and lower. And now I've gone all the way down to like 240. And of course, I'm going to keep messing with this till I break something. But as I really try to get it in the dark, I'm getting it down to 200 and something. But you know, with that glass lid in your thumb, it's very hard to get it completely dark. But you can see that I am really reading over a very large range from a couple of hundred up to 900 and something. So I'm really seeing an incredibly large and easy to read signal based on the kind of like reasonable light changes that we might be getting. Okay, so now it's kind of hard to look at that like that. So I want to show you something I don't think we've done before. What's very useful is if you'll come up here to tools, you see there's a serial plotter. And also what we can do is we can come over here, and you can't see that, can you? You can't see that. Let's see, how do I turn that nonsense off? Let's see. That was not good. I'll turn that back on. Okay, and I want to turn this off. Okay, now you can see it. this little thing turns on the serial plotter. So let's turn on the serial plotter. And then what you're going to have is you're going to have this thing pop up. Okay, this thing pop up. And you can see it's reading about 948. But then if I turn the light off, you see a big drop and turn it on. So you can see, I can see a very clear signal. I'm going from two very stable values, light on and light off. So the higher the light, the higher the voltage. The lower the light, the lower the voltage. But now I'm going to turn that off, and then I'm going to turn this off, and then you can see I'm way on down there, and I can close it like this. Now, what is the problem that we have? This plotter auto scales, and so you see now it looks like it's jumping up and around, but if you look at the axis, it has auto scaled, and that auto scale I absolutely hate. So let me show you how to get around that auto scale. What I can do is I can print, if I print a 0 and I print a 1023 and I have those going across, those two signals will keep you from auto scaling. So what am I going to do? I have light value, and now what I'm going to do, I am going to serial.print, no print ln, just serial.print. And what I'm going to do is, I need to do this a little different. Let's start with the light val. Okay, now after the light val, and I want to put all these numbers together, so I don't want this one to be a print ln this time. So I'm going to print the light value, which is our real data, and then I'm going to serial.print. And what am I going to print? Just a comma for a data separator. Okay, now what I'm going to do is I am going to serial.print. And what am I going to print? I am just going to print a 0. And then let's not forget our semicolons. Okay, so I printed a 0, and now I'm going to print another comma, serial.print, and then this time I'm going to print a comma. Now I'm going to do a serial.print ln, because now this is my last piece of data. So basically I'm printing 3 channels. Channel 1 is light val, a comma to separate the channels, a 0 is the second channel, and then a comma to separate the channels, and then the last thing that I'm going to print is 1023. And because I'm going to have a 0 and a 1023, any data that comes in, it's not going to auto scale. It's going to have the right scale for a signal from 0 to 1023, and that will turn off that silly auto scaling. And so now let's run this again. It is downloading. And now look, what you can see is I've got the real value, which is like the 783. Then I've got the next channel is 0 and the next channel is 1023. And now when I come over here, I've got the 0 and the 1023, and that is holding the vertical axis constant. So now let's turn some light on. We turn some light on and the voltage goes up. We turn the light off, the voltage goes down. We come over here and turn the desktop light on. It goes up even more, comes down, up, down, and then we can turn this all off, and then I can come in and cover it and see how low I can get this thing to go. You see, it's just, I can also become obsessive compulsive to see how dark I can get this thing. But you see, you could try this thing in the daytime and try this thing in the nighttime, and then see what you could get that to do. And I guess you didn't see me playing with that because I turned that off. Let me come back over here and turn that back on now. I should have had a second shot of that, but you see there, you can see it coming down and then coming back up and then coming down. I wonder if I move this over a little bit like that. Yeah, let me resize it a little bit. Okay, so now we go up, we go down, we go up, we go down. We turn this light on, and then we turn the studio lights on. And okay, so you can see a really strong and clear signal. Okay, this photo detector, it's a very simple little thing. And I know most of the lessons you see, they just take you in there and they just give you some code and show you a schematic and you hook it up. But I really want you to understand the solid state physics, because this thing that we learned about semiconductor devices, that is exactly how a computer works, and that's exactly how a transistor works, right? A computer is what? Bunch of zeros and ones. How do we get zeros and ones? We get zeros and ones by having switches. Okay, and then how do you turn the switch off? You get electrons up into that conduction band. How do you turn the switch off? You get the electrons back down in the valence band, and so this semiconductor, you switch it. Now, you don't switch it based on light in that case, but you can put a voltage on it that will kind of suck those electrons up into the conduction band, and then you can turn the voltage off and have them drop back into the valence band. And so then you can turn that switch on and off by putting a voltage on. Maybe I'll show you one day how a transistor works. That might be a little bit of fun. Okay, guys, I need to give you a homework assignment. What your homework assignment is to make some sort of visual display for the amount of light that you have. Like you might have an LED that changes color based on the brightness of the light. Or what I was thinking is you might have a little servo, and that servo would have a little pointer over a dial, and it could be pointing to a sunshiny day, pointing to a cloudy day, pointing to a like moonlight, and then pointing to a complete darkness. So you could have a servo visually show you how much light you were detecting, or you might do it with something like LEDs. And so I'm not telling you how you can do it, but I've given you two ideas, and your homework is to make some visual representation of the amount of light that's being detected. Again, if you get this DVM, make sure you get the little packet of wires, the little packet of extra types of connectors, and I've got both of those links down in the description. I hope you guys are having as much fun taking these lessons as I am making them. I want to give a shout out to you guys who are helping me out over at Patreon. My Patreon supporters are what keep this content coming. I'm able to stay in the game because you guys stand with me on Patreon. You can also help me by giving me a thumbs up and putting a comment down below. Also, be sure to subscribe to the channel. When you do, make sure that you ring that bell so you'll get notification of future lessons dropping. And most importantly, share this video with other people, because the world needs more people thinking like an engineer and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.